Hey everyone, Elmo from the future here. Just going to give a brief introduction on what this video is about, because I didn't really like the introduction that I gave in the actual recording. So this video is about a combinatorial sum. I originally posted to Q and Cube 3's channel, and then it was afterwards, after like 5 months, it was posted to the Dr3213 Discord server, and that's where I came across it. They decided to use complex analysis for God knows why, and I didn't like that idea, so here's another way. Hope you enjoy. Here's a method by which to solve this without using the binomial theorem, because that's kind of cheating, using the binomial theorem. So first off, we can deduce that x choose y, well, not really deduce, but it's a common theorem. X choose y is equal to x factorial divided by y factorial divided by x minus y factorial, right? So now, our next step is, we're going to convert this into gamma notation, so we can actually work with the values. Sorry about that. Okay, so it's going to be gamma of x plus 1 divided by gamma of y plus 1. And then, okay, so it's going to be gamma of x minus y plus 1. Okay, yeah, x minus y plus 1. Okay, good. And so now, what we're going to do is substitute 2k for the x and substitute k for the y. And so, by doing that, it gives you gamma of 2k plus 1 divided by gamma of k plus 1, and then times gamma of 2k minus k plus 1. Okay, so that's just going to be this. So it's just gamma of 2k plus 1 divided by the gamma of k plus 1 squared. Okay, so now, next we're going to do is, we're going to use Legendre's duplication formula, of which states that the gamma of 2z, I'm going to get on my knees for this. Okay, so gamma of 2z is equal to 2 to the 2z minus 1 times gamma of z times gamma of z plus 1/2, all divided by square root of pi, or gamma of 1/2. And then you could find a Pockhammer notation, but no, we're not going to do this. It's not hypergeometric series. Okay, so by applying this, well, you can, or actually, first off, we're going to have to factor out a 2 from the gamma in the numerator. So then we get gamma of 2 times k plus 1/2. And so then all divided by k factorial squared. Okay, so now what we can do is we apply the Legendre's duplication formula to this. Sorry about that. Okay, so then we get 2 to the 2 times k plus 1/2, then minus 1 gamma. Okay, so it's going to be the gamma of k plus 1/2. And then it's going to be the gamma of k plus 1/2, so gamma of k plus 1, all divided by root pi times gamma of k plus 1 squared, which is gamma of k plus 1 k factorial, right? Okay, so this square term is going to cancel out with that gamma of k plus 1 in the numerator, and so then that's going to yield a nice formula for the 2k choose k. So then we get, also you can simplify this down, this turns into 4 to the k. Just simplify that down. So this is going to equal 4 to the k times gamma of k plus 1/2, all divided by root pi k factorial. Okay, so you have two options now, or, well, okay, after you put it inside the sum, let's just put it inside the sum. after putting it inside the sum and substituting it, from 0 to infinity, we get, okay, 4 to the k, so then it's going to be 4 over 5 to the k. So 4 over 5 all to the k. And then gamma of k plus 1/2. All divided by square root of pi, and then k factorial. Okay. So now you have two bridging paths. Bridging paths. I don't know if that's okay. Yeah, you have two options now. You could either go down the hypergeometric series path, or you could substitute for this gamma of k plus 1/2. You could substitute the integral form of it. And so if you remember the integral definition of the gamma, you get gamma of x is equal to integral from 0 to infinity for e to the minus t, then t to the x minus 1 dt. That's the integral form. So if we were to substitute gamma of k plus 1/2 for this integral form, then we would get of k plus 1/2 is equal to the integral from 0 to infinity e to the minus t, then t to the k minus 1/2 dt. There we go. Okay, so our next move is going to be just substitute this in. And that gives us sum k equals 0 to infinity, or 1 over root pi, I should say. Here, factor out the 1 on root pi. 1 root pi, 4 over 5 to the k, divided by k factorial, then the integral from 0 to infinity for e to the minus t, and then t to the k minus 1/2 dt. So now what we can do is we can factor out everything that doesn't have to do with the sum outside of the sum. And so then we could just say that this is equal to the integral from 0 to infinity for t e to the minus t, then t to the minus 1/2 times the sum as k equals 0 to infinity. So now what we have here, we're going to have t to the k, so for 4 over 5 to the k, and then t to the k. Just checking for convergence here. Yeah, it converges, thank God. Yeah, that converges. And then divided by k factorial dt. So now that's a basic exponential, right? So what you can do is that, that's just a basic exponential. And that gives you e to the 4t over 5. So then that gives you finally the integral from 0 to infinity, or 1 on root pi times the integral from 0 to infinity for e to the minus t, and then e to the 4 over 5t, and then t to the minus 1/2 dt. Combine these two factors, that gives you t to the minus 1, that gives you e to the minus t over 5. So you can rewrite this whole thing. It's just going to turn to e to the minus t on 5, and then that's going to be t to the minus 1/2 dt. Okay, and lastly, what we can do is, or what we are going to do is, we're going to let we're going to put in terms of the gamma function, let u equal t over 5, du equals dt over 5. So, okay, du equals 5 dt. Okay, so then multiply by 5. So then you have 5 on root pi times the integral from 0 to infinity for e to the minus u. And then what you're going to have here, so you're going to have t equals 5u, so then you're going to have 1 on root 5. So then you would have 5 divided by root 5, so that's just going to be root 5. Okay, and so, yeah, that's about it. It's going to be e to the minus u, and then you're going to have u to the minus 1/2 du. So, what does that finally yield? I just going to confirm this is all accurate. Yeah, 1/5 dt, yep, that makes sense. So finally, we know what this is. This is just going to be the gamma of 1/2, which is square root of pi. So finally, we get a solution to be the square root of 5. Because we would have the gamma of 1/2 divided by root pi. So it's just going to be, here, I'm going to simplify it a little bit more. It's going to be square root of 5. It's not square root of pi. Jesus Christ, I'm tired. Okay, it's going to give us square root of 5 divided by square root of pi times gamma of 1/2, which is equal to square root of 5. But, oh my god, I keep on writing pi. Jesus, that's a 5. Divided by root pi, and times root pi. Both these terms just cancel. That gives you the square root of 5. Final answer. Okay, and that's about it. I thought... Yeah, I thought this method was a lot easier. A lot easier. So, yeah, that's why I used it. Hope you enjoyed. Yeah, that's about it. See you later then.